Start with a couple announcements, including one that is a little different from usual. So class-related announcements, those are the important ones. Homework due tomorrow. I have office hours today and tomorrow, both in the morning and the early afternoon, to handle whatever demand exists for that. This is a more challenging assignment, even though it's worth a bit fewer points than the last couple. So I hope to see you and be able to answer your questions. I'm still hoping to have exams for you tomorrow. We'll see. Then the strange announcement. FAST reached back out to me. So FAST, company that hires a few Eastern graduates every year, and they're interested in speaking in classes. But considering there's significant overlap between classes where they have talked and my students in here who've seen them talk in a past class, I wanted to make sure that I asked the class first before dedicating 10 minutes of our class time to a presentation of theirs. So is there anyone who would be interested in seeing a presentation from FAST and getting some information about the company with regards to potential future employment afterwards? So a couple of them, 1, 2, 3, sure. All right. If there's even a little bit of interest, I feel like it's probably worth it, considering someone who was in compilers last quarter actually applied, got a position, and is going to be working for them this year. So that's cool. So I'll respond to the positive for this class. For whatever overlap there is between this class and game dev, I'll be asking it again in game dev. But I think the people who answered in the positive, for the most part, aren't in that class. All right. Any questions before we dive into content? I'm having the phlegmiest morning. I don't know what's going on. If I hack up a hairball halfway through this lecture, don't worry. All right, last time we were talking about kind of the applications of context-free grammars and parse trees. They're all related. They represent the same class of language, the context-free language, and they have a lot of use in the compiler construction process with regards to syntax. So in fact, that's the answer to the first question that's on this slide. What aspects of a programming language would be modeled by a context-free grammar? It's everything related to syntax. What was syntax, or the difference between syntax and semantics? It might have been a while since you heard those terminologies and thought about that. So can someone explain that difference for the class? Syntax versus semantics.
Syntax is the rule of the rules of the language.
The rules of the construction of,
Yeah.
the ordering, what words exist, and kind of the structure of a rule that makes sense. What was semantics?
That would be what the code does.
It's close. It is the meaning behind the syntax. So sometimes you can create syntactically correct sentences that have no meaning. An example in English would be you start with a noun, you move into a verb phrase, and it has absolutely no meaning. The calculator flew to Mars. Perfectly valid English sentence. But when you think about it, it doesn't. I suppose it has some meaning. You could say the calculator flew to the center of the earth, and now we're very confused. It doesn't actually mean anything. Or you can even create gibberish. But they follow the legal words of the language, but doesn't have meaning. So different concerns between syntax and semantics. In programming languages, something like a perfectly legal syntactic statement is something like, char C equals the string hello. We have a legal assignment, we have a legal statement, but the meaning of it, we can't fit a string into a character variable. It's not something that we can actually do. It's not actionable. So we create that distinction between syntax and semantics, and we will handle them very differently in the compilation process. But for syntax, we're just trying to say, can we generate that statement via this grammar? So grammars don't make any claims about what is feasible or not, whether there are type clashes, something like that. But we'll talk about that in more detail when we talk about the pipers. Just want to make sure that we know the right area we're talking about when we mention syntax here. So, well, I really should read my slides before I go into tangents, because that is the very next thing that I was going to talk about. An example of something that a grammar can't model is semantics. Something like a perfectly legal syntactic sentence. Char C equals, let's go with the double this time, 3.2. And it is syntactically correct. But the fact that we can't put a floating point number into a character variable is a semantic rule. It's not a syntactic rule. So we could, with a grammar, generate something like this. However, we need an additional piece of logic to check whether there are type clashes. In general, semantics are a harder problem, so we're not going to think about them for now. We're going to hone in on syntax, because we still need to solve the syntax problem, and the syntax problem is extremely important. And in fact, there is nothing as simple as a context-free grammar for something like semantic analysis. We need more than that. It turns out that we need to have a tree and kind of move one process from the top of the tree down, one process from the bottom of the tree up, meet in the middle, and determine what real value is there. So what is the right-hand side of the expression? What does that evaluate as? What is the left-hand side expecting? And we're not necessarily going to know that until we meet that point in a program. And that creates a bit of a challenge with regards to how we parse that, how we come to that, identify those type clashes. Yeah, several methods proposed, nothing universally accepted for the most part. And ongoing discussion that you could contribute to if this is a problem that intrigues you. On to the next. This is one of the shortest slide decks that I made for this. It's all of 4 slides, including the motivation slide. But yeah, we're getting into simplification. How do we actually go simplify context-free grammars? I hinted at this yesterday when talking about it, but there are a couple other aspects of context-free grammars that we're going to want to be able to simplify. Beyond the couple of rules that we said, we could start to have some conclusions of context-free grammars on if we didn't allow those production types. We said we can always avoid a non-terminal to non-terminal production and a non-terminal to lambda production with intelligent finagling of the grammar. So we just talked about membership and parsing, and we're going to talk more about that as we dive into more efficient membership algorithms. But we looked at the feasibility of brute force parsing and concluded that it was garbage. Garbage. And that we need more efficient methods. But in preparation for those more efficient methods, we need to figure out what we can do with context-free grammars. In general, they have no restrictions on the production construction. The non-terminals can go anywhere. There can be an unlimited number of them. But what can we do to restrict the right-hand side of the context-free grammar productions without reducing the power of them and improving the efficiency when we go back to prepare for this? So let's talk a little bit about transforming grammars. How can we transform grammars? So we know there's not just one grammar that generates a language. You can create usually an infinite number of grammars that represent the same language. They can have different numbers of productions, different numbers of non-terminals, the same number of terminals, but maybe they're repeated in different ways. There are more or fewer of those same number of terminals. So one thing we could do is if the empty string is accepted, we could factor out the ability to just represent that. There's a simple rule for doing that. You make a new rule that says now that the new rule can go to lambda, but once we hit the original production, then we know it's not there. So we've factored it out of the original context-free grammar, creating a special rule for the empty string. Once we go to S, then it's the same grammar that we had before. So we can use the substitution rule as well. So when we have productions in a form where we have a terminal, a non-terminal, followed by a terminal, so it's a non-terminal surrounded by two terminals on either side, then the non-terminal can be replaced with all possible productions of that non-terminal. Let's give you an example. So here, the AB capital BC is a non-terminal that's surrounded by two terminals. We can create two rules where we would have the B arrow something, and we can throw that directly back into the production for capital B and eliminate it. Show you how that's done. So do we agree that there's no other branching factor in this production other than this non-terminal right here? Everything else is constant. So you can imagine basically taking this and now forking it, saying this could be any possible definition of that B. Actually, I'm going to draw this out horizontally rather than vertically. We could fork this to, instead of AB capital BC, we replace the capital B with its definitions. So we would have AB, B, capital A, C. Or we could have AB, B, C. And these become two new rules that replace this rule. So we get rid of this rule. And since now there's no other capital B anywhere in this, we could actually remove this entire non-terminal and sequence of productions and replace all of that with B's. So that's the substitution rule. You're just going back a recursive layer and now saying we're going to take the options that we had here and replace them as options here. And that's only a safe thing to do if that is a non-terminal that is surrounded by terminals. As soon as you have a non-terminal followed by a non-terminal, you start to have combinatorics. You can have combinations of the definition of one and the definition of the other. And now the number of productions that you need starts to blow up in ways that usually aren't worth using the substitution rule. It still can be done, but the end result is not always a simpler grammar. So there's also a procedure for removing unnecessary productions that we can see. Once we do this, we can see that we can get rid of the peak productions. Yeah.
What about one where T1 or T2 aren't there?
So it's the very beginning or the very end.
Yeah.
Yeah. So that in that case, you basically have the empty terminal, and you should safely be able to do that. So it could also be empty. That is a great question. Questions on this? So let's talk removing unnecessary productions. Let's give you an example here. Here's a grammar, but what do we notice about it? Is there anything interesting about this grammar that we could conclude that a simpler grammar exists?
We have a non-terminal surrounded by terminal.
We do.
Also, A versus A, capital A, seems pointless.
Yeah. Why? What is the issue with that? That is what I want to get at here. Why is that weird? Or
Like not providing any information that, or like it's not important information that A and then A goes to A, we just say S goes to A, capital A, or S goes to A.
I think we can even conclude more. How many strings that are in the language this grammar accepts go through that production? Let's draw it out. Let's say we'll take the shortest possible path. We'll start with S. The S becomes an A, so we can quickly get into that A. That A now has to become an A with a capital A at the end. This capital A now has to become an A with a capital A at the end. This A has to become an A with a capital A at the end. What's the issue? There's no possible path to termination. We've reached what is basically an infinite recursion or an infinite loop with no way of breaking out of it. So it actually doesn't add anything to this language. No strings that this grammar accepts go through that production, because every time you hit that production, you go into an infinite loop. So whenever we can identify a production that doesn't add anything to the language, we can safely remove it. It represents the same language as it does if we were to just get rid of all of it, everything that refers to it and everything that it does. Creates the exact same language. So to identify these things, we're going to use exactly what I just said as a definition. So a useful production says that it appears in at least one derivation for a sentence in the language that's accepted by the grammar. We have to have some path to produce something in the language via that production. If there are 0 of those, then we can safely remove it. It doesn't add anything to the definition of that grammar. The opposite is a useless production. A non-terminal cannot derive any sentence in the language via any sequence of its productions. And if that is the case, we can remove it. Making this general production is useless if it cannot be reached from the start state or if it can't derive a terminal string. Makes sense. Shall we dive into a practice problem? Here's a grammar. Let's go through this and simplify removing unnecessary productions. All right, what's useless here?
It's
B and C? Why is B useless?
never referenced anywhere.
Yeah, there's no non-terminal B anywhere on the right-hand side of anything in this grammar, which means that we've defined something that we never use. So it adds no string to the language. Why is C a useless production?
It never terminates.
It creates an infinite loop again. We have a non-terminal referring to itself in a way that has no way of producing just terminals or lambda or something that causes termination. So whenever we reach this C, it is only ever going to expand and expand and expand and never reach a string that we can say is in the language. So because of that, C can go and every reference to C can go. We could also substitute here a little bit, where we have this non-terminal with lambda on either side, basically. Since this only has a single definition, there's no reason to make a variable that represents just a terminal. That's kind of like making an object that just refers to a single value. You might as well use that value. Or an object that only has a single method. Granted, there are some cases where that exists in a design pattern for a valid reason, but there's a larger scope to that. When you have a grammar like this with a single thing, you might as well take this definition and just move it up there. So I'm going to get rid of this and just make this an A. And now we have a much simpler grammar that is just S arrow A capital S or lowercase a. That's it. Everything else we got rid of. Makes you realize that there was a ton that we didn't need here. So you find yourself creating grammars, it might be worth just a little bit taking a look and seeing if there are some useless productions in your grammars. Before I erase that, I should have asked her any questions. Anything I can describe in more detail? So we looked at which productions can't lead to a terminal string, that was C. Which productions can't be reached at all via a simple path from a starting state or from the start non-terminal. You can look at this like a dependency graph in terms of just, are there transitions? Are there definitions, productions such that the right-hand side of that production reaches something and is reached in some capacity? We could see that B is not reached algorithmically by making this transition graph. And again, when the example is this small, we can just look at it ourselves and see it. But if you're dealing with a very large grammar or a grammar with lots of rules and dependencies and XORs, it might actually benefit us to be able to see that we created something that wasn't excessive. It's easier to do in much larger examples for much larger problems. Why would we not convert ACB to ASB? Because then we would be allowing for elements of the language that shouldn't be there. So if we converted this to ASB, then we could go S arrow C arrow ASB arrow. This A now can become that's a string that cannot be produced by this grammar in any capacity. There's no way to actually produce a B in our simplified grammar, but when we turn it into this, we're allowing for a string that otherwise wouldn't have been there. So it is not an equivalent grammar. Good question. That was it. That was the 5 slides. Good job, everyone. I should really put that into some other slide deck. It's not really its own This one, on the other hand, is a good bit longer. This is actually going to completely lead up to our first programming project in the class. By the time we are done with this, we will be ready to implement something. This is exciting. You took this class, and I told you at the beginning it was going to be very much like a math class, but it's a math class with a couple of projects that apply these ideas and remind you that it is, in fact, a computer science class. All right. This is almost the same motivation as before so far. We can convert grammars into grammars of other forms, but in fact, there are some normal forms that all grammars, all context-free grammars can be converted into, and some of those forms are necessary for some of the optimizations that we're going to be making. So if we want to solve the syntax problem in an efficient way, we need to have some restrictions on our grammars that ensure that productions are in particular forms. So there are two we're going to look at. The first and most directly applicable to us is Chomsky normal form. And Noam Chomsky appears everywhere in computer science, wherever he was actually an English professor, but wherever syntax, semantics appear in programming languages, all of that comes from language theory. So Chomsky appears wherever that is. So as long as we can take lambda out of a grammar, we can make a grammar in CNF, which is Chomsky normal form. So we talked about how to factor a lambda out of the grammar completely, which is good. We'll need to use that if we see lambda in a grammar. Then it places restrictions on numbers of terminals and non-terminals in each production. But it's pretty straightforward, which is nice. It's not an incredibly difficult process. And we end up with a form that we can feed right into the algorithm that will be your first programming project. So the first important part of this is going to be conversion into CNF. There is also Greibach normal form. And similar, any context-free grammar without lambda has an equivalent form in GNF. And GNF is used for conversion from grammar form to state machine form. And we're going to talk about how to represent context-free languages in a state machine form after we talk about this. So that's where GNF will come back to us. And this just places restrictions on the terminals and non-terminals positions with respect to each other. Conversion, not quite as straightforward, but we'll come back to it. We'll start honing in on CNF. All right, two possible forms in CNF. We can have a non-terminal that becomes two non-terminals. And we can have non-terminal into a single terminal. And in fact, that is it. Those are the two legal forms of productions in a CNF grammar. So go ahead and write one. Write a grammar with at least 4 productions adhering to CNF, just to make sure that you get a sense of those rules. Make sure that this grammar that you make has no useless productions. Anyone have a grammar they want to share? Yes. Let's see something. What you got?
S to capital AB.
Capital A, capital B?
Yeah.
Okay.
Then A goes to just the lowercase a.
Mm-hmm.
The B goes to capital C, capital D. And then C goes to a single B. And D goes to a single C.
That works. 5 productions. They all adhere to this form, and each one is used for something. Not a particularly interesting grammar in that we can make AB, which is A followed by BC. So ABC is in the language. And that's it. But hey, it works. The legal CNF grammar. Questions on the form of anything? There tend to be a lot more productions in CNF than there are in other forms, as we will see. All right, so conversion into CNF. That's a much more interesting question. Let's figure out how to take an arbitrary context-free grammar and convert it into CNF. So input to this algorithm is a grammar, and there cannot be lambda or productions where the right-hand side is a single non-terminal. But we have talked about how to deal with both of these. We can factor out the lambda, and we can also use substitution to factor out where we have right-hand sides of a single non-terminal. We can replace wherever on the right-hand side that appears with its associated form, and then get rid of it. So we're going to assume from here on out that the grammar we have adheres to both of those input restrictions. So we've discussed how to remove them. So if you see a grammar with them, make sure that you adhere to that before you begin this conversion process. So we are going to be constructing a new grammar from the input grammar. So we start with an empty grammar, and we are going to begin making rules for that empty grammar based on the rules in the input. So let's start by looking at all productions of the form. There's a non-terminal and some list of terminals and or non-terminals. We should look at the size of the list. The size of the list is 1, it must be a terminal, because if it were a non-terminal, then we would have had to do something with it in the input restriction. And if it is a single terminal, it already adheres to CNF. Non-terminal arrow terminal is one of the legal rule types. So beyond that, we are going to introduce new non-terminals for every terminal in the production. And have that non-terminal go to that terminal, and only that terminal. That is a rule in CNF that we can do. So we need each terminal to be represented by one of those new non-terminals. For each of those non-terminals introduced, add a production that converts the non-terminals to their associated terminal in the new grammar. And now, if we look back, there are no terminals in any production in any right-hand side with length more than 1. All that's left are rules of non-terminal arrow list of non-terminals or non-terminal arrow terminal. And that is it. So we go back to the original grammar and we do that replacement where of terminals for their non-terminal forms in the new grammar, making sure that we have just that non-terminal arrow bunch of non-terminals. So we could break down each one of those productions into its individual non-terminal components. So n sub 1 is the first non-terminal, n sub 2 is the second non-terminal, up to n sub l, which is the length of the production non-terminal. So we're going to break this down into further and further. We're going to do this process recursively. We're going to break this down into introducing a new non-terminal that represents the last L-1 characters and the first non-terminal. And that becomes a production of the form non-terminal arrow, non-terminal, non-terminal. One non-terminal represents a single letter. The rest, the other non-terminal represents the other L-1 non-terminals. Then we recurse on that and break that down into its first and the remainder. Recurse on that, break it down into the first and the remainder. And at the end of this process, we have a grammar completely in CNF. So then remove all old productions that aren't in CNF in the old grammar, and we should have the resulting grammar being in CNF. This is much easier to visualize rather than see as an algorithm or set of rules. So let's dive into an example and show how it works. So for this grammar, we want to, first step, introduce non-terminals that represent the terminals. So we are going to, for the moment, just do that. Let's say we have C arrow A, D arrow B, and E arrow C. Step 2 is we're going to backpropagate the non-terminal representation of each of these terminals into all of these rules where they appear. So where we see a B, that's going to become a D. Where we see an A, that's going to become a C. Where we see an A, that's going to become a C. Where we see a B, that's going to become a D. Where we see a C, that's going to become an E. So every production now is of the form either non-terminal arrow terminal or non-terminal arrow a bunch of non-terminals. So now we need to begin recursively breaking these down so that we have only non-terminal arrow, non-terminal, non-terminal. So B is already in the appropriate form. B arrow capital A capital E is already in a form that CNF is okay with, no work is needed there. But each of these others have a little bit of work that we need to do. So we're going to make a new form for this that says we are going to kind of collapse this DC into a new non-terminal. So we're going to make an F arrow capital D capital C. And then we're going to replace this capital D capital C with that F. Similarly, we're going to take this CD, that is the second part of this, we're going to make a new production, G arrow, capital C, capital D, and we're going to backtrack and replace that with a G. And we are done. The algorithm makes it look way harder than it is in practice. It's pretty intuitive. Thinking about it in just those 3 steps, make the productions for the terminals, backtrack, replace all terminals in the grammar with those non-terminal representations, then recursively go through for every production that is longer than 2, and recursively break it into the components that is the first non-terminal and everything that is left over. Then you're going to make a non-terminal for the everything that is left over and recurse that process on that until you end up with productions that are all just 2 non-terminals. And every one of those will eventually break down into a sequence of 2s. And the end result will be in CNF. Any questions on that process? How do we feel about it? Show of thumbs. Does it make sense? Kind of sort of makes sense. Let's get the rest of these on there. Here's some other way to think of it. So variables to get the first 2 productions in the normal form, and then you end up with a result. And that is equivalent to what I did, even though the names are different. Let's do another example. I don't have another example, so I'm going to make another example. All right, so let's convert this into CNF. I'm going to give you a few minutes to work on this. Created this off the top of my head, trying not to make any useless productions. It has no meaning, but I wanted to make something long enough that there is that recursive process. Feel free to work with neighbors, or if you are isolated, find some neighbors to work with. Get you started. handle the S production. That was a fun recursive process, but we got there. Something for this. This creates an interesting dilemma, the fact that we have a DC that we want to make here, but we already have a DC here. Is there a way to reutilize this? The answer is currently no, because we have to turn this DC into a single letter and we can't have that. So we can either make the DC, but one other thing that we can note is we can actually take the DD off the front as well and make that into something, so it doesn't have to recurse on the back, it could recurse on the front. Doesn't really matter. So I'm just going to take it back. What's fun here is when we have an option like this, we can actually turn one into one that already exists. This BA up front is a BA, the definition that we already have. So instead of making a new non-terminal for AC, which isn't anywhere in this, we can actually reuse G here and recurse in the front. So we can get rid of the BA and turn that into a G and make it ever so slightly simpler. So here's an answer. It is not the only answer. It is just an answer. Questions on this process? We're a little bit over time, so if you want to pack up in the meantime, you have somewhere to be, feel free to start doing that. Any questions I can answer about going through the process of converting this into that? Right, we'll come back tomorrow, hopefully be going over exams, and if not, or when we finish, we'll start talking about GNF.
Do you know if homework 2 is going to be graded as soon as
It was supposed to be graded earlier this week. It was the first item on that to-do list for the year, so it should be done relatively soon. I do apologize for the delay. I know it's been. It should have been done by now.
I have a question about the.
Yeah,
DCC here, wouldn't this be paid here?
you could, but it wouldn't be a legal production in CNF. You replace it with J, but then you have A arrow J, which doesn't work.
There needs to be 2 of these.
Yeah, there needs to be 2. So it is possible to create a rule that would short. Yeah, you just don't use it because it has to stay on that one. Even though it seems like it's suboptimal, or that it should be shorthanded in some capacity. After that shorthand.
Because that confused me a bit, because I remember seeing DC.
Yeah.
How did you make that?
Yeah.
It's
Good question though. That's a trickier element of this. Yeah, it doesn't look optimal, but it has to adhere to this form. We will see why when we go optimize the syntax and parsing process.
Factors
Yeah.
are greater than 2.
Exactly, but.
So if you construct it, should be 2